Frameshift drive charging. 4, 3, 2, 1, engage. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Cannot comply. 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 Landing gear deployed. Landing gear retracted. Cannot comply. Frameshift drive charging. Ready to engage. 4, 3, 2, 1. Engage. Surface scanned by 50%. Surface scan complete. Surface scanned by 50%. Surface scan complete. Module malfunction. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. disengaged. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. System scan complete. Fuel scooping. Fuel scoop disengaged. Frameshift drive charging.
Light is the fastest thing in the universe. Nothing outruns it. A single photon crosses from Earth to the Moon in 1.3 seconds, reaches Mars in 3 minutes, and exits our entire solar system in a matter of hours. It seems impossibly fast. But here is the terrifying truth scientists rarely say out loud. Light is slow, agonizingly, hopelessly slow. So slow that even traveling at its absolute maximum, a beam of light launched today toward the nearest star would not arrive for 4 years and 3 months. So slow that an alien civilization with technology a million years ahead of ours would still need decades, centuries, or millennia to physically reach Earth. The speed of light is not a bridge between worlds. It is a prison wall, and we are all locked inside. If you are ready to see why the universe may have made contact between civilizations nearly impossible, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making deep dives like this one. Now, let's begin. Light moves at 670 million miles per hour. Nothing in the universe travels faster. Not particles accelerated in the most powerful colliders on Earth. Not the shock waves from collapsing stars. Not the radiation streaming off a supernova at the moment of detonation. Light occupies the absolute ceiling of physical velocity, a speed limit woven into the architecture of space and time by the laws of physics themselves. Einstein proved it in 1905. Every experiment since has confirmed it. The speed of light is not just fast, it is the fastest anything can ever be. And on human scales it feels like magic. Right now, light is completing a task so rapid it makes every other speed in nature seem frozen. A single photon, leaving a flashlight in your hand, reaches the wall across the room in roughly 10 billionths of a second. That same photon, if fired horizontally across the surface of the Earth, would lap the entire planet 7.5 times in a single second. In the time it takes your brain to register the sensation of touching a hot stove, light has already travelled from New York to Los Angeles and back roughly 10 times. The speed is so extreme that for most of human history, scientists genuinely debated whether light moved at all or simply appeared everywhere instantaneously. It was not until 1676 that Danish astronomer Ole Romer calculated a finite speed for light by observing the moons of Jupiter. He noticed that the timing of eclipses shifted depending on whether Earth was moving toward Jupiter or away from it. The difference was caused by light needing extra time to cross the changing distance. His work was groundbreaking, and when Christian Huygens later used Romer's data to calculate a numerical value, the result was roughly 227,000 kilometers per second. Imprecise, but it shattered the idea of instantaneous illumination. Light was fast, unimaginably fast, but it was not infinite. Modern instruments have refined Romer's measurement to extraordinary precision. Light travels at exactly 299,792.458 kilometers per second in a vacuum. Scientists know this number so precisely that they actually use it to define the meter itself. 1 meter is the distance light travels in 1,299,792,458th of a second. The speed of light is not merely measured, it is the ruler against which all other measurements are made. On the scale of everyday experience, this speed is overwhelming. Consider the moon. It hangs in the sky roughly 239,000 miles from Earth. Light crosses that gap in 1.3 seconds. When the Apollo astronauts spoke to mission control from the lunar surface, their words travelled at light speed via radio waves, and the delay was barely noticeable. A conversational pause, a slight hesitation, nothing that would suggest the signal had just crossed 250,000 miles of vacuum. Now extend the beam to the Sun. Our star sits approximately 93 million miles away. Light covers this distance in 8 minutes and 20 seconds. When you step outside and feel the warmth of sunlight on your face, Those photons left the sun's surface before you started brushing your teeth. The sun you see in the sky is not the sun as it exists right now. It is the sun as it existed 8 minutes ago. If the sun vanished this instant, you would continue to see it shining for 8 more minutes before the sky went dark. You would feel its warmth. You would see its light. And all of it would be a ghost. This delay is so short that it barely registers in human consciousness. 8 minutes is trivial. We wait longer for a cup of coffee. But it represents the first whisper of a problem that will grow louder and more terrifying as we push farther into space. Mars, at its closest approach, sits roughly 34 million miles from Earth. Light reaches it in about 3 minutes. At its farthest, when Mars and Earth are on opposite sides of the Sun, the distance swells to 250 million miles, and light needs roughly 22 minutes. NASA mission controllers already feel this delay acutely. When the Perseverance rover encounters an obstacle on the Martian surface, the signal reporting the problem takes minutes to reach Earth. The command to stop takes minutes to travel back. By the time instructions arrive, the rover has been driving blind for the better part of half an hour. Even at the speed of light, Mars is far enough away that real-time control becomes impossible. Jupiter lies roughly 484 million miles from the Sun. Light needs about 43 minutes to make the trip. Saturn sits at 886 million miles. Light takes roughly 79 minutes. By the time you reach Neptune, the outermost major planet at approximately 2.8 billion miles, light requires over 4 hours to arrive. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object in space, so far away that a signal from it, travelling at the speed of light, takes approximately 22 hours to reach us. Nearly a full day for a message moving at the fastest speed in the universe. 22 hours. Nearly a full day. And Voyager 1 has not even left the neighbourhood. It has barely crossed the boundary where the sun's influence fades and interstellar space begins. In nearly 5 decades of travel, covering 15 billion miles, Voyager 1 has traversed less than 1/400th of a single light year. This is where the illusion begins to crack. A light year is the distance light travels in 1 year of continuous motion. That's 670 million miles per hour, running non-stop for 365 days. Light covers approximately 5.88 trillion miles. That number is so large that writing it out in standard form requires 13 digits, 5,880 billion miles, and it represents the basic unit of interstellar measurement, the smallest meaningful increment when talking about the distances between stars. The nearest star system to our Sun is Alpha Centauri, a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and their distant companion Proxima Centauri. Proxima Centauri is the closest of the three, sitting approximately 4.24 light-years from Earth. That translates to roughly 25 trillion miles. Let that number settle for a moment. 25 trillion miles. Light, the fastest thing in the universe, needs 4 years and 3 months to cross this gap. A beam of light leaving Earth right now will not reach the nearest star until sometime in 2030, and this is the closest star, the nearest one, the galactic equivalent of the house next door. In 2016, astronomers confirmed the existence of Proxima Centauri b, a roughly Earth-mass planet orbiting within the habitable zone of Proxima Centauri. The discovery electrified the scientific community because it meant there was a potentially rocky world receiving enough energy from its star to possibly support liquid water, right next door in cosmic terms. The planet orbits its red dwarf host once every 11.2 Earth days, sitting far closer to its star than Mercury does to our Sun. Whether Proxima Centauri b actually harbours conditions suitable for life remains deeply uncertain. Its star is a flare star, prone to violent bursts of ultraviolet and X-ray radiation that could strip away any atmosphere. The planet is likely tidally locked, with one face permanently baking and the other frozen in eternal night. As of 2025, We still do not know if it has an atmosphere at all. But the crucial point is not whether Proxima Centauri b is habitable. The crucial point is where it is. 4.24 light-years, 25 trillion miles. Even if it were a perfect twin of Earth, teeming with oceans and oxygen and life, light itself needs more than 4 years to bridge the gap. A radio message sent today would not arrive until 2030. A reply, if anyone were there to send one, would not reach us until 2034 at the earliest. A simple hello and response would consume nearly a decade, and Proxima Centauri is the closest candidate we have. Move outward and the numbers become savage. Barnard's star, the next nearest single star, lies roughly 5.96 light-years away. Recent observations have confirmed planets orbiting it, but none yet confirmed to sit in the habitable zone. Ross 128 sits about 11 light-years away and hosts a planet that may be temperate. Teagardens star, roughly 12.5 light-years distant, hosts Teagardens star b, a world that scored near the top of the Earth Similarity Index when it was discovered in 2019, with a surface temperature estimated near 20 degrees Celsius. That score was later revised downward, but it remains one of the most Earth-like candidates known. Yet light needs 12.5 years to reach it. A radio signal sent in 2026 would arrive in 2038. The TRAPPIST-1 system grabbed global headlines in 2017 when astronomers announced 7 roughly Earth-sized planets orbiting a single ultra-cool red dwarf star, with at least 3 sitting in or near the habitable zone. It was and remains one of the most promising multi-planet systems for studying habitability. But TRAPPIST-1 sits approximately 40 light-years from Earth. Light leaving Earth the year you were born would still not have arrived there if you are under 40 years old. A message sent at the speed of light, the day World War II ended in 1945, would just now be pulling into the system. 40 light-years. That is roughly 235 trillion miles, and in galactic terms, it is still absurdly close. The Milky Way spans at least 100,000 light-years in its visible disk alone. Some recent measurements suggest it may extend to 200,000 light-years or more when you include the outer stellar halo. The galactic center lies approximately 26,000 light-years from Earth. Light that left the center of our galaxy when early humans were painting caves in Europe has still not reached us. It will arrive in roughly 24,000 more years. The galaxy contains an estimated 200 to 400 billion stars. Among those, astronomers now believe that a significant fraction host planets. Statistical analysis of Kepler Space Telescope data suggests there could be billions of Earth-sized planets orbiting in habitable zones throughout the Milky Way. Billions of potential homes for life. Billions of worlds where, in principle, water might pool on rocky surfaces and chemistry might inch toward biology. But those 40 billion worlds are scattered across a disk, 100,000 light-years wide. The average distance between neighboring star systems in our region of the galaxy is roughly 4 to 5 light-years, and in the dense central bulge, stars pack more tightly, perhaps a light-year or 2 apart. In the sparse outer arms where we live, the gaps widen, and the habitable worlds among those stars are not evenly distributed. They are sprinkled randomly across this enormous volume, separated by gulfs measured in light-years, tens of light-years, hundreds of light-years. Here is where the true nature of the speed of light reveals itself. Light is not fast in any meaningful interstellar sense. It is agonizingly, almost comically slow. A photon leaving Earth and heading for the center of the Milky Way will not arrive for 26,000 years. A photon heading for the far side of the galaxy will need 100,000 years. A photon aimed at the Andromeda Galaxy, our nearest major galactic neighbor, will require 2.5 million years to arrive, and these are photons, massless particles, traveling at the absolute maximum speed the universe allows. The speed of light feels fast because humans evolved on a planet 8,000 miles wide, orbiting a star 93 million miles away. On those scales, light is instantaneous for all practical purposes. You flip a switch and the room illuminates. You look at the moon and see it as it was 1.3 seconds ago, a delay no human can perceive. Even the 8-minute delay from the sun is invisible in daily life. But the moment you try to use light speed to connect two star systems, the illusion collapses. The speed that seemed infinite on Earth becomes a crawl between stars. The fastest possible velocity in nature becomes a barrier, not a bridge. It is like discovering that the fastest car ever built can cross a parking lot in a blink, but needs centuries to cross a continent. This mismatch between light's perceived speed and its actual utility over interstellar distances is the central trap of the cosmos. It creates a universe where intelligent civilizations can look up, observe billions of stars, detect the signatures of potentially habitable worlds, and calculate that the galaxy should be teeming with life. But it simultaneously means that reaching those worlds, physically traveling to them, requires confronting a speed limit so restrictive that even the nearest destinations demand timescales measured in decades, centuries, or millennia. And here is the detail that tightens the trap even further. We have been talking about light speed, the theoretical maximum, the absolute ceiling. No material object with mass has ever been accelerated to light speed. No spacecraft, no particle in a collider, no atom in nature reaches that limit. Objects with mass require infinite energy to reach the speed of light. It is not a practical barrier. It is a physical impossibility. The laws of physics encoded in Einstein's special relativity guarantee that any object with mass, no matter how small, can approach the speed of light but never touch it. This means that any physical spacecraft, whether built by humans or by an alien civilization a billion years more advanced, will always travel slower than light. The travel times we have been calculating at light speed are not realistic estimates. They are absolute minimums, theoretical flaws, the fastest possible case. Real travel times will always be longer, usually much longer. Voyager 1, currently humanity's most distant emissary, moves at roughly 17 kilometers per second. That is about 1/17,600th the speed of light. At that velocity, Voyager 1 would need approximately 75,000 years to reach Proxima Centauri. 75,000 years. Human civilization in its entirety, from the first agricultural settlements to the present day, spans roughly 10 to 12,000 years. Voyager 1 would need to fly for 6 times the entire length of recorded human history just to reach the nearest star. Even the fastest spacecraft humanity has ever built, the Parker Solar Probe, skimming the sun at velocities that dwarf anything else in our engineering history, would need thousands of years to cover interstellar distances. These are not theoretical machines from a science fiction novel. These are the real, physical spacecraft we have launched, with the best technology available. And they are comically inadequate for interstellar travel. The gap between what light can do and what our machines can do is not a small engineering shortfall. It is a chasm, spanning 4 orders of magnitude. Light is roughly 17,000 times faster than Voyager 1. To close even a fraction of that gap, a spacecraft would need propulsion systems that generate energies far beyond anything humanity has ever produced. This realization changes the way we must think about the Fermi paradox, the famous question posed by physicist Enrico Fermi in 1950. If the galaxy is so old and so vast and contains so many potential sites for life, where is everybody? The standard answers range from suggesting that intelligent life is exceptionally rare, to proposing that civilizations inevitably destroy themselves, to speculating that aliens are hiding or observing us without contact. But there is a simpler, more physically grounded answer hiding in plain sight. The speed of light itself may be the explanation, not because it prevents civilizations from existing, not because it prevents them from developing advanced technology, but because it prevents them from crossing the distances between stars in any practical time frame. The galaxy may be full of intelligent civilizations, each one looking up at the same sky, detecting the same candidate worlds, dreaming of the same interstellar journeys, and running into the same merciless wall. The speed of light is 300,000 kilometers per second. It sounds fast because it is fast, locally, on tiny scales, in the narrow arena of human experience. But the cosmos does not operate on human scales. It operates on scales where light years are the small unit and galaxies are the medium one. On those scales, the speed of light is not a superpower. It is a leash, a short one. And every calculation we are about to make will show why that leash makes physical interstellar travel not just difficult, but potentially impossible for any civilization that has ever existed or ever will exist in this galaxy. The illusion of speed has one final cruel twist. Because light is also the fastest way to observe the universe, every civilization discovers the cosmos long before it can ever hope to visit it. Telescopes reveal billions of stars. Spectrometers detect the chemical fingerprints of distant atmospheres. Radio dishes listen for signals across the electromagnetic spectrum. An intelligent species can map the galaxy in exquisite detail, catalogue thousands of potentially habitable worlds, and confirm that the raw ingredients for life exist in abundance everywhere it looks. But seeing is not reaching, observing is not arriving. The same speed of light that carries information to our telescopes also sets the upper bound on how fast we could ever physically travel to the sources of that information. The universe lets you look, it lets you wonder, it lets you calculate and dream and plan. And then it tells you the nearest interesting destination is 25 trillion miles away, and nothing you build will ever get there in less than a human lifetime, using any technology that currently exists or is plausibly achievable within the laws of physics. The light that brings us knowledge of the stars is the same light that measures the distance we can never cross. It is simultaneously the messenger and the prison guard, the revealer and the wall. What comes next reveals why even the most ambitious attempts to close this gap run into a barrier that grows worse the harder you push against it. The travel times are only the beginning of the problem. The energy required to achieve those travel times transforms interstellar flight from an engineering challenge into something far more daunting, a confrontation with the fundamental limits of physics itself. Voyager 1 left Earth on September 5, 1977. It carried a golden record etched with sounds and images of human civilization, a message in a bottle tossed into the cosmic ocean. Nearly 5 decades later, it remains the most distant human-made object in existence, sailing through interstellar space at roughly 17 kilometers per second, about 38,000 miles per hour. In everyday terms, that is blisteringly fast. A commercial airplane cruises at 550 miles per hour. A bullet leaves a rifle at roughly 1,700 miles per hour. Voyager 1 travels more than 20 times faster than a bullet every second of every day, without slowing down, without stopping, for almost half a century. And it has covered an almost meaningless fraction of the distance to even the nearest star. In 47 years of continuous flight, Voyager 1 has travelled approximately 15 billion miles. Against the distance we established earlier, Voyager 1 has completed about 0.06% of the journey. If it were pointed directly at Proxima Centauri, which it is not, it would arrive in approximately 75,000 years. That is not a typo. 75,000 years. To put that in context, 75,000 years ago, modern humans had not yet left Africa in significant numbers. The last ice age had not yet reached its peak. Woolly mammoths roamed across Europe and Asia. The entirety of what we call civilization, every empire, every invention, every written word, every war, every symphony, every scientific discovery, fits inside the last 10,000 years. Voyager 1 would need to fly for 7.5 times that span just to reach the nearest star. This is the baseline. This is where humanity currently stands in terms of interstellar capability. Not close, not within reach, not approaching viability. We are so far from interstellar travel at current speeds that the timescales involved exceed meaningful comprehension. Voyager 1 will be a frozen, silent relic drifting through black emptiness for millennia, after human civilization has either transformed beyond recognition or cease to exist entirely. But what if we could go faster? What if we could build spacecraft that dramatically exceed Voyager's velocity? How much faster would we need to go before interstellar travel becomes even remotely plausible? Let us begin climbing the speed ladder and see what happens. At 1% of the speed of light, a spacecraft would travel at approximately 3,000 kilometers per second, or about 6.7 million miles per hour. This is roughly 176 times faster than Voyager 1. It is a speed so extreme that no human-built object has come anywhere close to achieving it. The Parker Solar Probe, the fastest spacecraft ever flown relative to the Sun, peaked at roughly 190 kilometers per second during its closest solar passes. 1% of light speed is nearly 16 times faster than that. At this velocity, a journey to Proxima Centauri would take approximately 425 years. That is shorter than Voyager's 75,000-year estimate by a factor of almost 200. It sounds like progress. But 425 years is still an enormous span of time. When Columbus crossed the Atlantic in 1492, the journey took about 2 months. A 425-year mission to Proxima Centauri would mean that if a ship had launched during Columbus's era, it would still not have arrived. The crew who launched the mission would have been dead for centuries. Their grandchildren would have been dead for centuries. The civilization that built the ship might not even exist anymore by the time it reached its destination. Reaching Teegarden's star at 1% of light speed would take roughly 1,250 years. The TRAPPIST-1 system, at 40 light-years, would require 4,000 years. 4 millennia. That is older than the Egyptian pyramids. A spacecraft launched at 1% of the speed of light toward TRAPPIST-1 at the dawn of ancient Egypt would still be in transit today, with another 2,000 years of travel remaining. 1% of light speed is not nearly fast enough. Push to 5%. At 5% of light speed, roughly 15,000 kilometers per second, or about 33.5 million miles per hour, the numbers start to compress. Proxima Centauri drops to roughly 85 years. Teegarden's star falls to about 250 years. TRAPPIST-1 shrinks to 800 years. These are still multi-generational timescales, but for the nearest targets, we are finally approaching something that overlaps with a long human lifespan. An astronaut who departed at age 20 might, in theory, arrive at Proxima Centauri at age 105. Unlikely to survive the trip, but at least the journey fits within the outer boundary of biological possibility. The problem is that 5% of light speed represents an almost incomprehensible engineering leap. No propulsion system ever built or seriously tested comes close. Chemical rockets, the technology that powers every spacecraft humanity has ever launched, top out at exhaust velocities of roughly 4 to 5 kilometers per second. Ion engines, like those used on the Dawn spacecraft, achieve higher exhaust velocities but produce minuscule thrust, suitable for slow spirals through the inner solar system, not for interstellar sprints. Nuclear thermal propulsion, studied extensively during the NERVA program in the 1960s, offers roughly double the efficiency of chemical rockets. Still, nowhere near enough. Even fusion-powered spacecraft, which remain entirely theoretical, would struggle to reach 5% of light speed. The most optimistic designs from the Project Daedalus study conducted by the British Interplanetary Society in the 1970s envisioned a massive unmanned probe weighing 54,000 tons at launch, using inertial confinement fusion to accelerate to about 12% of light speed. But Daedalus was never more than a theoretical exercise. No fusion engine capable of sustained thrust has ever been built, and the fuel requirements were staggering. The probe would have needed 50,000 tons of deuterium and helium-3, a fuel that exists in such small quantities on Earth that harvesting sufficient amounts would likely require mining the atmosphere of Jupiter. Push to 10% of light speed. Now the numbers become more tempting for the nearest targets. Proxima Centauri at 10% light speed takes roughly 42 years. A mission launched when an astronaut is 25 years old arrives when they are 67. Difficult. brutal on the human body after decades in microgravity and confined spaces, but within a single human lifetime. This is the threshold that many researchers identify as the minimum viable speed for a crewed interstellar mission to the nearest star. But look beyond Proxima Centauri and the trap reasserts itself. Teagardens star, at 10% light speed, takes 125 years, 2 full human lifetimes. TRAPPIST-1 takes 400 years. Any star beyond about 15 light years requires multi-generational timescales, even at 10% of light speed. And 10% of light speed is 30,000 kilometers per second, a velocity so extreme that the engineering challenges are nearly as daunting as the distances themselves. What about 20%? The Breakthrough Starship project, announced in 2016 with $100 million in funding from physicist and investor Yuri Milner and supported by Stephen Hawking and Mark Zuckerberg, aimed to accelerate a spacecraft to 20% of the speed of light. At that velocity, Proxima Centauri would be reachable in roughly 21 years. A message sent back at light speed would arrive at Earth about 4 years later. Total mission time from launch to data return, approximately 25 years. This is genuinely within a single human career. A scientist who helps launch the mission in their 30s could analyze the results in their 50s. But the Breakthrough Starship design was not a crewed vessel. It was not even a traditional probe. It was a gram-scale chip, a spacecraft weighing about 1 gram, roughly the mass of a paperclip, attached to a meter-scale reflective sail. The plan called for an array of ground-based lasers with a combined output of 100 gigawatts to fire at the sail for roughly 10 minutes, accelerating the chip to 20% of light speed through sheer radiation pressure. The spacecraft would carry a tiny camera, basic sensors, and a minimal communication system. It would fly through the Alpha Centauri system in a matter of hours, snap a few images, and attempt to transmit them back to Earth using an onboard laser powered by the energy it could collect. Even this minimal concept proved overwhelmingly difficult. By September 2025, Scientific American reported that the Breakthrough Starship project had been placed on indefinite hold. Of the $100 million pledged, only about $4.5 million had actually been spent across roughly 30 contracts. The engineering challenges were simply too severe. The laser array required gigawatt-scale power that no existing facility could provide. The sail material needed to be almost perfectly reflective, because absorbing even a tiny fraction of 100 gigawatts of laser energy would vaporize it instantly. The chip needed to survive acceleration forces of thousands of G and then endure 40 years of interstellar space, including bombardment by dust grains that at 20% of light speed would impact with the energy of small explosions. Communication back to Earth from 4 light-years away using a chip-sized transmitter presented unsolved problems in signal power and beam coherence. And this was for a paperclip mass flyby probe, not a crewed ship, not a landing mission, not even a probe that could slow down in orbit. A 1-gram chip screaming through the Alpha Centauri system at 60,000 kilometers per second, getting a few hours of observation before vanishing into the interstellar void forever. If 20% of light speed is this difficult for 1 gram of payload, the implications for anything heavier are devastating. Consider what a meaningful interstellar mission would actually require. Not a chip, a spacecraft capable of supporting scientific instruments, communication equipment, a power source, shielding against interstellar dust and cosmic radiation, and potentially a deceleration system. Even a modest unmanned probe designed to enter orbit around a target star would need to mass hundreds or thousands of kilograms. A crewed vessel capable of supporting human life for decades would mass tens of thousands of tons at minimum, accounting for life support, food, water recycling, radiation shielding, medical facilities, and the psychological requirements of keeping a crew functional during a journey lasting longer than most careers. The relationship between payload mass and the difficulty of reaching interstellar speeds is not something that scales kindly. There is a reason that no realistic interstellar mission profile ever proposes sending a crewed vessel at anything close to the speed of light. And that reason comes down to a fundamental equation in rocketry that we will confront directly very soon. For now, it is enough to understand the core principle. The fuel needed to accelerate a heavier spacecraft itself adds mass, which requires more fuel, which adds more mass. The faster you want to go, the more fuel you need, and the more fuel you carry, the heavier you become, which demands yet more fuel. This cascading penalty turns interstellar speeds into a problem that does not merely grow with ambition, it explodes. This is why no realistic interstellar mission profile ever proposes sending a crewed vessel at anything close to the speed of light. The energy and fuel costs do not scale kindly, they scale mercilessly. But the travel time problem has another dimension beyond raw speed, one that is easy to overlook but equally devastating: biological lifespan. Every organism we know of has a finite life. Humans, even under the best medical conditions available today, rarely survive past 110 or 120 years. The average lifespan in developed nations hovers around 80 years. A mission to Proxima Centauri at 10% of light speed takes about 42 years, survivable in principle for a young, healthy crew. A mission to a star 20 light-years away at the same speed takes 200 years. No human alive today, and no human who will be born under currently understood biology, can live that long. This biological clock applies not only to humans but almost certainly to any biological organism that might evolve elsewhere in the galaxy. While we cannot know the lifespans of alien species, the fundamental constraints of biology suggest that all carbon-based life faces thermodynamic limits on longevity. Cells accumulate damage, DNA degrades. Metabolic processes generate waste products that eventually overwhelm repair mechanisms. Even if an alien species lives 5 times longer than humans, say 500 years, a mission lasting 1,000 years at 5% of light speed to a star 100 light-years away still exceeds their biological window. The standard response to the biological lifespan problem is to propose generation ships, vessels large enough to sustain a self-reproducing population across many generations. The crew that launches the mission is not the crew that arrives. Their descendants, born and raised entirely aboard the ship, complete the journey. This concept has been explored extensively in science fiction and has received some serious academic analysis. The challenges are monumental. A generation ship would need to be a fully self-sustaining ecosystem, recycling all air, water, and nutrients indefinitely. It would need to support a population large enough to maintain genetic diversity across centuries, which geneticists estimate at a minimum of several hundred to several thousand individuals. It would need energy sources capable of running for millennia without resupply. It would need social structures robust enough to maintain mission coherence across dozens of generations, preventing internal conflict, cultural drift, or the simple loss of institutional knowledge about why the mission exists and where it is going. No human organization has ever maintained a coherent institutional mission for more than a few centuries. Religions and some governmental structures come closest, but even those undergo radical transformation over spans of 500 or 1,000 years. The idea that a ship-based civilization could maintain a coherent objective across 30 or 50 generations, with each new generation choosing to continue a journey they never chose to begin, requires a level of social engineering that has no historical precedent. Suspended animation offers a theoretical alternative. If crew members could be placed into a state of metabolic suspension, their biological clocks effectively paused, they could survive journeys lasting centuries. Science fiction routinely depicts this technology as cryogenic freezing, where passengers are cooled to near absolute zero and revived upon arrival. In reality, no technology capable of reversibly freezing and reviving a complex multicellular organism exists, and the obstacles are formidable. Water expands when it freezes, rupturing cell membranes. Ice crystals shred delicate tissue structures. Even vitrification, a rapid cooling technique that avoids ice crystal formation, has been demonstrated only in very small tissue samples and individual organs under laboratory conditions. Whole body suspended animation for humans remains firmly in the realm of speculation. But even if a spacecraft could somehow carry its crew across decades or centuries, whether through biological endurance, generation ships, or suspended animation, it still must survive the journey itself. And interstellar space, far from being a passive vacuum, is an actively hostile environment that degrades everything passing through it. The space between stars is not truly empty. It contains the interstellar medium, a thin haze of hydrogen atoms, helium, trace heavier elements, and dust grains. The average density is roughly 1 atom per cubic centimeter, a vacuum far more extreme than anything achievable in a laboratory on Earth. But at relativistic speeds, even this whisper of matter becomes lethal. A spacecraft traveling at 10% of the speed of light moves at 30,000 kilometers per second. At that velocity, every hydrogen atom in the interstellar medium impacts the spacecraft's forward surface with the kinetic energy of a high-energy particle. The cumulative effect is equivalent to standing in front of an intense beam of radiation. Engineers working on the breakthrough starship concept calculated that at 20% of light speed, the interstellar medium would deliver a radiation dose to the spacecraft's leading surface comparable to the inside of a particle accelerator. Over years and decades of transit, this bombardment would degrade electronic components, erode structural materials, and slowly destroy any unshielded surface. Dust grains present an even more dramatic hazard. The interstellar medium contains microscopic solid particles, silicates, carbon compounds, ice crystals, typically measuring fractions of a micrometer across. On Earth, these would be invisible to the naked eye. But kinetic energy scales with the square of velocity. A dust grain massing 1 nanogram, a billionth of a gram, striking a spacecraft at 10% of light speed carries kinetic energy equivalent to roughly 450 joules. That is comparable to the muzzle energy of a small handgun round. A single invisible speck of interstellar dust would punch through the hull of any conventional spacecraft like a bullet through paper. At 20% of light speed, the energy quadruples. Each dust grain impact becomes equivalent to a rifle round. Over a journey lasting decades, a spacecraft would encounter millions of such particles. The cumulative damage would be catastrophic without shielding far more massive than anything currently achievable, and every kilogram of shielding added to the spacecraft increases the total mass, which increases the fuel requirement, which compounds the rocket equation penalty we have already discussed. Cosmic rays add another layer of degradation. These high-energy particles, primarily protons accelerated to near light speed by supernova shockwaves and other astrophysical processes, permeate the galaxy. On Earth, our atmosphere and magnetic field shield us from the worst of them. In interstellar space, there is no such protection. Cosmic rays penetrate spacecraft hulls, ionize atoms in electronic circuits, corrupt data stored in computer memory, and damage biological tissue. Over the course of a multi-decade mission, the cumulative radiation dose from cosmic rays alone poses severe risks to both living crew and electronic systems. NASA has studied the effects of cosmic radiation extensively in the context of Mars missions, which would expose astronauts to elevated radiation for roughly 2 to 3 years. The findings are sobering. Extended exposure increases cancer risk, damages the central nervous system, and may accelerate cognitive decline. Studies on rodents exposed to simulated cosmic ray environments showed measurable brain inflammation and impaired memory. An interstellar mission lasting 40 or 80 or 400 years would subject its crew or its electronic systems to radiation doses orders of magnitude higher than a Mars mission. Without shielding far beyond current capability, the crew would face cumulative biological damage that no medical intervention could reverse. And then there is the slow, relentless decay of the spacecraft itself. Every mechanical system degrades over time. Seals crack, lubricants evaporate, metal fatigues. Electronic components drift out of specification. On Earth, we maintain complex machines through constant repair and replacement of parts. The International Space Station, the most complex structure ever built in space, requires continuous resupply from Earth and constant maintenance by its crew. It has been operational for roughly 25 years and already shows significant wear. An interstellar spacecraft would need to operate for decades or centuries with no resupply, no replacement parts from external sources, and no possibility of rescue if something fails. Every component must either last for the full mission duration or be repairable using only materials and tools carried on board. This demands engineering margins and redundancy levels that no human project has ever achieved. The longest operating spacecraft in history, the Voyager probes, have survived roughly 5 decades, and both are experiencing progressive instrument failures as their radioisotope thermoelectric generators decay and their electronics age, extending that operational lifespan to centuries or millennia under the additional stresses of relativistic dust bombardment and cosmic radiation represents a challenge without precedent. These environmental hazards do not merely add inconvenience to the travel time problem, they compound it fundamentally. Long travel times are not just boring or logistically difficult, they are actively destructive. The longer the journey, the more damage the spacecraft accumulates, the more likely a critical system fails, and the lower the probability that anything functional arrives at the destination. The interstellar medium is not a passive stage on which the drama of travel plays out. It is an adversary, eroding the mission with every passing year. There is also the problem of what happens to the civilization that launches the mission. Suppose an alien species sends a generation ship toward a star 100 light-years away at 5% of light speed. The journey takes 2,000 years. During those 2,000 years, the home civilization continues to exist, to develop, to advance. Technologies improve. New propulsion methods may be discovered. Faster ships may be built. It is entirely possible, perhaps even likely, that a ship launched centuries after the original would overtake the generation ship and arrive first. The original crew or their descendants would arrive to find the destination already colonized by their own civilization's later efforts. This is sometimes called the weight calculation, or the incessant obsolescence problem. It suggests that launching an interstellar mission before propulsion technology is sufficiently mature is not just wasteful, but actively counterproductive. You are better off waiting until you can go fast enough that no future ship will beat you there. But this creates an infinite regress. There is always a reason to wait for better technology. The mission never launches. The combination of extreme travel times, biological mortality, generation ship complexity, interstellar environmental hazards, and the obsolescence problem creates a devastating trap for any civilization contemplating interstellar travel. Even if you can build a ship that reaches 10% of light speed, the number of accessible targets within a single biological lifetime is vanishingly small. Perhaps a handful of star systems within 20 or 30 light years. Beyond that radius, every mission becomes multi-generational, demanding social, engineering, and survivability solutions that may be fundamentally unachievable. And the galaxy is not 30 light-years across. It is 100,000 light-years across at minimum. The vast majority of stars, the vast majority of potentially habitable planets, the vast majority of wherever alien civilizations might exist, sit at distances that require travel times spanning thousands, tens of thousands, or hundreds of thousands of years, even at ambitious fractions of light speed. Let us make this concrete with a specific example. Suppose an alien civilization exists around a sun-like star in the Sagittarius arm of the Milky Way, roughly 30,000 light-years from Earth. They are technologically advanced. They have mastered fusion propulsion and can accelerate a large spacecraft to 5% of the speed of light, a capability far beyond anything humans currently possess. They aim their ship at Earth. At 5% of light speed, the journey takes 600,000 years. 600,000 years ago on Earth, Homo sapiens did not yet exist. Neanderthals were still hundreds of thousands of years in the future. The dominant hominids were Homo heidelbergensis, a species most people have never heard of. The continents were in approximately the same positions they occupy today, but the climate was radically different, oscillating between glacial and interglacial periods. The entire arc of human evolution, from the emergence of our species in Africa to the construction of particle accelerators and space telescopes, fits comfortably inside the travel time of this hypothetical mission. If that alien civilization launched their ships 600,000 years ago, it would be arriving right about now. But what are the odds that a civilization maintains the institutional will, the technological infrastructure, and the physical resources to support a 600,000-year mission? What are the odds that the ship itself survives 600 millennia of interstellar space, enduring micrometeorite impacts, cosmic ray degradation, mechanical wear, and the slow decay of every material component? Even if we grant generous assumptions about alien engineering, the timescales are crushing. A civilization capable of building a ship that lasts 600,000 years would need to be stable across a span of time that dwarfs the entire history of complex life on Earth's land surfaces. That is not an engineering problem. That is a question about the fundamental nature of civilizational persistence. Whether any organized society, biological or otherwise, can maintain coherence across geological time. Push the numbers further. A civilization on the far side of the galaxy, 90,000 light-years away, attempting to reach Earth at 5% of light speed, faces a journey of 1.8 million years. At 10% of light speed, 900,000 years, even at the wildly optimistic speed of 50% of light speed, a velocity that would require energy expenditures beyond any plausible projection, the trip takes 180,000 years. The Milky Way is roughly 13 billion years old. It has had plenty of time for civilizations to arise, develop, and attempt expansion. But the speed of light ensures that crossing the galaxy is not a matter of centuries or even millennia. It is a matter of hundreds of thousands to millions of years. Each journey is a civilizational marathon with no guarantee that the runners will still be alive or still be civilizations when they reach the finish line. This is the travel time trap. It is not a single barrier, but a series of compounding constraints. Distances are enormous. Achievable speeds are a tiny fraction of light speed. Travel times exceed biological lifespans for all but the nearest targets. Generation ships face engineering and social challenges with no proven solutions. The interstellar environment actively degrades every spacecraft that enters it. The obsolescence problem discourages launching missions at suboptimal speeds, and the galaxy is so vast that even relativistic travel times stretch across geological epochs. The trap applies equally to any civilization, regardless of how advanced it is. An alien species with 1 million years of technological development still faces the same speed limit. They still cannot exceed the speed of light. They may build faster ships than we can imagine, but those ships will still travel at some fraction of light speed, and the distances remain unchanged. No amount of technological progress can shrink the galaxy. No amount of engineering brilliance can make Proxima Centauri closer than 4.24 light-years, or make the galactic center closer than 26,000 light-years. The speed of light does not discriminate between primitive and advanced civilizations. It constrains all of them equally. And for the vast majority of star systems in the Milky Way, the travel times it imposes are so extreme that physical contact between civilizations becomes not merely difficult, but functionally impossible within any reasonable definition of a mission, a lifespan, or a civilization's continuity. But the travel time trap is only half the story. We have been calculating how long interstellar journeys take. We have not yet asked the question that makes the problem exponentially worse. How much energy does it cost to reach those speeds? The answer is where interstellar travel transitions from merely impractical to something approaching physical impossibility. The energy wall ahead is higher than most people can imagine, and what sits behind it is even worse. Every spacecraft ever launched by human civilization has been powered by controlled chemical explosions. Liquid hydrogen and liquid oxygen combine in a combustion chamber, producing superheated steam that blasts out of a nozzle at roughly 4.5 kilometers per second. The rocket moves forward. Newton's third law in action. This is the technology that carried the Apollo astronauts to the moon, that lofted the Hubble Space Telescope into orbit, that delivered rovers to the surface of Mars. It works brilliantly for reaching Earth orbit and navigating the inner solar system. It is laughably inadequate for interstellar travel. The reason comes down to a single concept that governs all of rocketry: exhaust velocity. A rocket moves forward by throwing mass out the back. The faster that mass is ejected, the more efficiently the rocket converts fuel into speed. Chemical rockets eject exhaust at roughly 4 to 5 kilometers per second. To reach a final velocity significantly higher than your exhaust velocity, you need exponentially more fuel. This relationship is captured in the Tsiolkovsky rocket equation, derived by Russian scientist Konstantin Tsiolkovsky in 1897, and it is the single most important equation in spacecraft design. The equation is deceptively simple. The final velocity of a rocket depends on the exhaust velocity multiplied by the natural logarithm of the ratio between the rocket's initial mass and its final mass. What this means in practice is devastating. If your exhaust velocity is 5 kilometers per second, and you want to reach 50 kilometers per second, you need a mass ratio of roughly 22,000 to 1. For every kilogram of payload you want to deliver at that speed, you need 22,000 kilograms of fuel at launch, and 50 kilometers per second is pathetically slow by interstellar standards. It is less than 0.02% of the speed of light. At that velocity, reaching Proxima Centauri would take approximately 25,000 years. To reach even 1% of the speed of light, 3,000 kilometers per second, with a chemical rocket, the mass ratio becomes a number so large it has no physical meaning. You would need more fuel than exists in the observable universe to accelerate a single kilogram to 1% of light speed using chemical propulsion. This is not an exaggeration. It is arithmetic. The exponential nature of the rocket equation makes chemical rockets fundamentally incapable of interstellar travel at any meaningful speed. This is why every serious proposal for interstellar propulsion abandons chemical energy entirely and looks to nuclear physics. Nuclear reactions release roughly 1,000,000 times more energy per kilogram of fuel than chemical reactions. A kilogram of uranium undergoing fission produces about 80 trillion joules of energy. A kilogram of hydrogen-oxygen propellant produces about 13 million joules. The difference is a factor of approximately 6 million. Nuclear energy offers a path to exhaust velocities that are orders of magnitude higher than chemical rockets, which dramatically improves the mass ratios required for high-speed travel. But even nuclear energy has limits, and those limits become visible disturbingly quickly when you start calculating the requirements for interstellar speeds. Consider the energy needed to accelerate a modest spacecraft to 10% of the speed of light. Let us define modest conservatively. Not a crewed vessel, not a generation ship. A robotic probe massing 1,000 kilograms, roughly the weight of a small car. This is far heavier than the breakthrough starship concept, but far lighter than anything capable of carrying humans or sophisticated scientific instruments. The kinetic energy of a 1,000 kilogram object moving at 10% of the speed of light is calculated using the relativistic kinetic energy formula. At 10% of light speed, relativistic effects are still small, so the classical approximation works reasonably well. 1/2 times mass times velocity squared. The velocity is 30 million meters per second. Squaring that gives 9 times 10 to the 14th. Multiply by 500, half the mass in kilograms, and you get 4.5 times 10 to the 17th joules. 4.5 times 10 to the 17th joules. That is 450 quadrillion joules. To put this in perspective, the total energy consumption of the entire United States in a year is approximately 1 times 10 to the 20th joules. The energy needed to accelerate a single small probe to 10% of light speed is roughly 1/200th of America's annual energy consumption. For one probe, weighing 1,000 kilograms, going only 10% of light speed, scale up to a more meaningful spacecraft. A crewed vessel capable of supporting even a small crew for a multi-decade journey would need to mass at least 100,000 kilograms, and that is an extremely optimistic estimate that ignores radiation shielding, redundant life support, and the structural mass needed to contain a pressurized habitat. At 100,000 kilograms, the energy requirement jumps to 4.5 times 10 to the 19th joules. That exceeds the annual energy output of most nations. Now push the speed higher. At 20% of light speed, the kinetic energy quadruples compared to 10%, because energy scales with the square of velocity. At 50% of light speed, the energy is 25 times higher than at 10%, and relativistic corrections begin adding significant additional cost. At 90% of light speed, the relativistic mass increase means the actual energy needed is many times higher than the classical formula would suggest. The total energy required to accelerate a 100,000 kilogram vessel to 90% of light speed exceeds 10 to the 22nd joules. That is roughly 20 times the total annual energy consumption of human civilization, concentrated into the propulsion of a single ship. These numbers are not theoretical curiosities. They represent hard physical constraints. Energy cannot be created from nothing. It must come from somewhere. Fuel must be carried, generated, or collected. And the more energy you need, the more fuel you must carry, which adds mass, which increases the energy requirement, which demands more fuel. The rocket equation's exponential penalty applies at every stage. This is why propulsion researchers focus so intensely on exhaust velocity. The higher the exhaust velocity, the less fuel you need for a given final speed. Fusion rockets, if they could ever be built, would achieve exhaust velocities in the range of 10,000 to 30,000 kilometers per second, roughly 3 to 10% of light speed. This dramatically reduces the mass ratios compared to fission or chemical rockets. A fusion-powered spacecraft reaching 10% of light speed might need a mass ratio of only 10 or 20 to 1, challenging but conceivable in principle. But no fusion engine capable of sustained, controlled thrust has ever been built. The entire field of fusion energy, despite 7 decades of research and tens of billions of dollars in investment, has not yet produced a commercially viable power plant on Earth, let alone a propulsion system capable of operating in space. The ITER experimental fusion reactor in France, the most ambitious fusion project in history, is designed to demonstrate net energy gain from fusion, but will not achieve full deuterium-tritium fusion operations until the late 2030s at the earliest, after decades of delays and cost overruns. It is a stationary building-sized facility. Converting fusion into a compact, reliable spacecraft engine that can operate continuously for years or decades represents an additional engineering leap of enormous proportions. Antimatter propulsion represents the theoretical upper limit of energy density. When a particle of matter meets its antiparticle, they annihilate each other completely, converting 100% of their combined mass into energy. This is vastly more efficient than any other known energy source. Fission converts roughly 0.1% of mass into energy. Fusion converts roughly 0.7%. Antimatter annihilation converts 100%. A single kilogram of antimatter annihilating with a kilogram of normal matter would release approximately 1.8 times 10 to the 17th joules, enough to accelerate a small probe to a meaningful fraction of light speed. The problem is producing antimatter. Current particle accelerators can create antimatter in vanishingly small quantities. The total amount of antimatter ever produced by all of humanity's particle accelerators combined is estimated at roughly 20 nanograms. Not 20 grams. 20 nanograms. 20 billionths of a gram. Producing even 1 gram of antimatter using current technology would cost on the order of tens of trillions of dollars and take millions of years of continuous accelerator operation. Producing the kilograms or tons needed for a starship is so far beyond current capability that it borders on the meaningless to discuss as a near-term option. But there is a deeper problem with antimatter that is rarely discussed and frequently misunderstood. Antimatter is not a source of energy. It is a storage medium, and it is a catastrophically inefficient one. Creating antimatter requires energy input. In particle accelerators, high-energy collisions produce particle-antiparticle pairs from the kinetic energy of the colliding particles. The process obeys conservation of energy with absolute strictness. To create a positron, you must invest at least the energy equivalent of the positron's rest mass, plus the rest mass of the electron created alongside it, plus whatever kinetic energy the collision products carry. In practice, the efficiency of current accelerators at producing antimatter is measured in billionths of a percent. For every billion joules of energy pumped into the accelerator, only a few joules worth of antimatter comes out. The rest is lost as heat, radiation, and kinetic energy of particles that do not produce useful antiparticles. Even a theoretically perfect process cannot beat break-even. The absolute minimum energy required to create an antiparticle is equal to the energy that antiparticle will release upon annihilation. You cannot get more energy out of antimatter than you put into making it. At best, you get the same amount back. In reality, you always get less, because no conversion process is perfectly efficient. Antimatter does not generate energy. It merely stores it in an extraordinarily compact form and returns a fraction of the original investment upon annihilation. This means that a civilization fueling an interstellar mission with antimatter must first generate all of the required energy through some other means, whether fusion, fission, stellar collection, or something else entirely. Then it must pay the enormous efficiency penalty of converting that energy into antimatter. Then it must store the antimatter without losses for the duration of the mission preparation and the journey itself, a period potentially spanning decades. The total energy infrastructure required to produce mission-ready quantities of antimatter would dwarf the energy content of the antimatter itself, potentially by orders of magnitude. Antimatter does not solve the energy problem of interstellar travel. It relocates the problem, wrapping it in an additional layer of inefficiency that makes the total energy budget even more punishing than the raw kinetic energy calculations suggest. Storage presents equally formidable challenges. Antimatter annihilates on contact with any normal matter. It must be contained in a perfect vacuum using magnetic or electric fields, a technology called a penning trap. Current traps can hold tiny numbers of antiparticles for limited durations, scaling this to contain macroscopic quantities of antimatter, keeping it perfectly isolated from the walls of its container and from stray gas molecules for the duration of a multi-decade mission, would require engineering breakthroughs that do not currently exist even in theoretical form. Laser sail propulsion, the approach chosen by breakthrough Starshot, sidesteps the fuel problem by leaving the energy source behind. Instead of carrying fuel, the spacecraft is pushed by a beam of light fired from a stationary installation. The spacecraft carries no propellant at all. Its mass can be minimized. The energy comes from a ground-based or space-based laser array, which can draw power from conventional sources. This approach has genuine theoretical advantages. It eliminates the tyranny of the rocket equation because the spacecraft does not need to carry its own fuel. The laser array can be scaled up over time, reused for multiple launches and powered by renewable energy. This is why breakthrough Starshot chose it as the most plausible path to relativistic speeds. But laser sails face their own devastating constraints. The laser array must deliver enormous power over enormous distances. Breakthrough Starshot envisioned a 100 gigawatt laser array, roughly equivalent to the total electrical generating capacity of a medium-sized country, focused on a sail only meters across. The beam must remain tightly focused across millions of kilometers as the spacecraft accelerates away from Earth. Diffraction, the natural spreading of light beams over distance, means that the array must be kilometers in scale to maintain a sufficiently tight beam, and the acceleration phase lasts only minutes. Once the spacecraft outpaces the beam's ability to push it, it coasts freely for the remaining decades of the journey. Most critically, laser sails can only push. they cannot pull. The beam accelerates the spacecraft away from the laser source, but it provides no mechanism for slowing down at the destination. A laser sail spacecraft arriving at Proxima Centauri at 20% of light speed would scream through the entire star system in a matter of hours and continue into interstellar space forever. It would be a flyby mission, not an arrival, not an orbit insertion, not a landing. A brief glimpse, then permanent departure. This brings us to the cruelest dimension of the energy problem: deceleration. Every discussion of interstellar travel speeds focuses on acceleration. How fast can we get going? But arriving at a destination requires stopping, or at least slowing down enough to enter orbit or conduct extended observations. And slowing down costs just as much energy as speeding up. If you accelerate a spacecraft to 10% of light speed, you must spend a certain amount of energy to reach that velocity. If you then want to decelerate to rest at the destination star, you must spend the same amount of energy again, applied in the opposite direction. The total energy budget for a mission that both arrives at speed and stops at its target is not double the acceleration energy. It is worse, because the fuel needed for deceleration must itself be accelerated during the first half of the trip, adding to the initial mass and compounding the rocket equation penalty.